Okay, let's look at the diesel cycle from an air standard uh, framework. So we're not going to assume that the specific heats are constant, in which case we're going to need to use the ideal gas tables. And if you look at the ideal gas tables for air, you'll notice that there's a column for temperature, and then we have enthalpy, internal energy, specific internal energy, and then we have the relative pressure and relative specific volume. And all these things can be found if we know the temperature, or we can vice versa. If we know VR or PR, we can find the temperature. So we'll start with, if we have T1, then we can find these other values. And one of the things we can find is VR1. Of course, if we're between temperatures in the table, we just interpolate. Then if we have some way from V1 to find VR2, then we can go this way and find T2. And for that matter, we can find a value for the enthalpy if we need it, and specific internal energy if we need it. Right? So we're going to do that approach. So what is this relationship? Well, one of these that we're going to use is that, so for an isentropic process, we can use these expressions. So V1 over V2 equals VR1 over VR2. And this is, VR1 is a function of T1. So if I know T1, I can find VR1. And VR2 is a function of T2. In this case, if I know VR2, I can find what temperature corresponds with that VR2. And V1 over V2 is our compression ratio. So that's R. So now I can solve for VR2. So VR2, which is a function of T2, equals VR1 divided by R. So I go to the tables with my T1. I find corresponding VR for that temperature. I divide it by my compression ratio. So if it was 10, I divide by 10, and then I get another VR. I find that VR in the table, and then I get whatever I need for that. So in this case, I would find the enthalpy or internal energy. So for process, if this is process 1, 2, I would then find, once I know VR2, I would find U2, which is from the tables, which is a function of T2, which now I know, or I can make it a function of VR2 if I want. And then I can also find U1, and in this case it's directly from T1 that I can find it without even finding VR. So one way I could write this is a function of VR2. So I'm going to first find U1 from T1, then find VR1 from T1, divide it by R, and that gives me VR2, and then I can look up U2. So that helps me with the first process. Then I need temperature 3. Temperature 3, air standard or cold air standard, it's still an ideal gas. So we have P3 V3 over P2 V2 equals T3 over T2. And that's just taking the ideal gas law, dividing it by the ideal gas law, and we had an R in there, but that canceled, just became 1. And then we note that, well, the pressure also cancels because P2 equals P3. And this V3 over V2 is what we call RC. So just like the cold air standard, we get the same relationship. So there's nothing about constant specific heats for this relationship. So it's only the isotropic process that was affected, with it being air standard or cold air standard. And we move on to T4. T4, we're going to follow the same process that we did for the first one. So what we need is to know what that ratio of volumes are. And the compression process is called R, and then it's going to equal the product of all the expansion ratios. So we have RC times, let's call this RV34. So then RV34 equals R divided by RC. So if we had 3 expansion processes and we knew the compression ratio for all of them, we would just multiply those 3 together, and that would equal the product of all the expansion ratios. So now I have that unknown expansion ratio RV34, and I can then write that V doesn't matter capital or lowercase, since it's a ratio. Let's write V3 do the larger over the smaller. So let me write that as V4 over V3, which is what I'm defining as RV34, which I know now, it's R over RC, equals VR4, which is a function of T4, over VR3, which is a function of T3. And then I can get that VR4, which is a function of T4, equals VR3 divided by, and then I can write RV34 or R for RC in this case. So now I get VR4 from things that I know, and then from VR4 I can find U4, T4, so U4 would be a function of VR4, and I think that's all I need. And I have U3 already and U4, now I can get the work for process 3-4. And then the final process should already have U1 and U4, and so I just put in values for that. So now I have the Q for each process, the work for each process, and then finally the efficiency is simply just 1 minus Q out over Q in. And I do need to recognize that this is going to be a negative value, so I would use the absolute value of this, since it's going to be negative in the numerator, and I've already made it negative in my equation. So put some numbers in, and you should be good for homework problem using the air standard method. Now, the air standard method is going to be a little more accurate than the cold air standard method, but then we also need to use the tables and interpolate, so it may take a little more time to do it.